our last learning standard of the semester is going to pull together all of the ideas that we've been talking about with normal subgroups and factor groups and cosets and the fundamental theorem of finite abelian groups. And it's going to unite that theory with the theory of isomorphisms, right, which is learning standard number 6 and also one of the chewiest learning standards in the course just because functions, right? So the way it's going to do that, this week is going to culminate in a very important theorem called the first isomorphism theorem. This is perhaps one of the most important structural theorems in all of abstract algebra. And I feel like I say that a lot. I certainly said it about Lagrange's theorem, and it was true then. But this one is important because it gives us a way to understand factor groups without having to go through all the explicit rigmarole that we've been going through up until this point, such as the rigmarole that you just went through on the quiz that we just finished up. So I want to pick up where that quiz sort of leaves off, or where it culminates. So on the quiz, I gave you a listing of all the elements of A4, just so there could be no confusion about what the group A4 is that we're talking about. And I gave you 2 choices of possible subgroup of A4. One of them was called, what was it? Did I call them H and K? And H had these 4 elements in it: identity, 1, 2 composed with 3, 4, 1, 3 composed with 2, 4, and 1, 4 composed with 2, 3. And then K just had 2 elements in it. It was just identity and 1, 3 composed with 2, 4. And so the first thing I asked you to do about these 2 subgroups was which one of them, when you list out all the cosets, let me say it this way, when you list out all of the cosets, which one of them did you find was a normal subgroup of A4? One of these is normal in A4. The other one is not normal in A4. H is normal. How come? You knew I was going to ask that.
Closure.
Okay.
And identity.
Closure, identity, inverses, all of that is true, but I would say that closure, identity, and inverses are all true of K as well. Right? 1, 3, 2, 4 composed with itself is the identity. Compose either of these with each other, and we get the same thing. Compose identity with itself, we get identity. Closure, identity, inverses, those are true in both H and K. They're both subgroups of A4. But why is H a normal subgroup and K is not? So it's easier, since I narrowed the universe for you, we have the option of, instead of proving H is normal, let's prove K is not. So why is K not a normal subgroup? What would be a way to investigate that question?
I took an element from A4 and then did the left and right and found that it wasn't in K.
That's a great idea. We can go directly to the definition of normal subgroup, which says, remember, the definition is that K is a normal subgroup of A4 by definition if for all elements, let's call them sigma, in A4, we have sigma K, the left coset of sigma, agrees with K sigma, the right coset of sigma. So this is a great way to disprove that for all statement holds. We just need a single counterexample which shows that the left coset need not equal the right coset. Do you remember what element you chose for sigma?
1, 4, 2 or 1, 2, 4.
Okay. So as an example, let's choose sigma equals 1, 2, 4. And then let's just find out what 1, 2, 4 does to the elements of K. Right. So sigma K, that's going to have the elements 1, 2, 4 times identity, comma, 1, 2, 4 times 1, 3, 2, 4. Right, and of course, this first element is just going to be 1, 2, 4 because we're multiplying by identity. But then we have to simplify out this second product. There probably should have been a standard 5 check on this quiz. I'll think about that as I'm grading it. So what does 1 do? 1 goes to 3, and then 3 stays put. So 1, 3. And then 3 goes to 1, which ends up at 2. 2 goes to 4, which ends up back at 1. And so that concludes my cycle. So that's what I get, at least for the left coset of K by this element. If I do the right coset, K sigma, well, the first element is going to be identity times 1, 2, 4, which I'm just going to skip the extra line here and just write that as 1, 2, 4 again. But the other element is going to be 1, 3, 2, 4 composed with 1, 2, 4. And when I simplify that out, let's see, 1 goes to 2, and then 2 goes to 4, and then 4 stays put. So 1 has gone to 4. I think already we can see this isn't going to work out. 4 goes to 1, which goes to 3. 3 goes to 1, and so that completes this cycle. So at the end of the day, we notice that these two sets are not equal, right? So this is clearly not a normal subgroup, right? Because those two elements are not common to both sets. So K is not a normal subgroup, and so if you believe me about the way that the problem is set up, then that must mean that H here is our normal subgroup of A4. But believe it or not, and this is why this last chapter is important and useful, it is generally a hard problem for me to give you a group and say, tell me all the normal subgroups in this group. It's kind of not that bad to try to tell me all the subgroups, if you understand what the elements are, how they interact, what some of the generators are. But to actually test for normality, it's kind of tricky. What we're developing this week is a better way, a third way, a way that lets us check for whether a subgroup is normal without having to recurse to the definition. And the definition is hard to prove true, right? Because we would have to prove for all sigma. And so I would have really 12 different proofs to do if we were really doing it one element at a time, right? We want a smarter way to test whether a subgroup is normal. And that's what the first isomorphism theorem is going to help us to do. It's not only going to help us to show that a subgroup is normal, but that theorem will also be able to tell us what is the structure of the factor group, okay? The group we get by quotienting out, by looking at the group of cosets. So let's take this, let's take and list out the cosets for this normal subgroup inside of A4. So obviously the trivial coset, the coset of the identity, is just these 4 elements. It's H itself. What's an example of a non-trivial coset in A4 of this subgroup, if you're listing these out? So how am I going to get a non-trivial coset of this subgroup in A4? What should I do? Well, same story as we did over here, right? Pick an element of A4. And as long as it's not one of the elements that's already been listed up here, if I form the left coset of H by that element, I'm going to get a left coset of the subgroup that's not equal to the original subgroup. So go pick an element of A4 that's not already in this group. I don't know. How about 1, 2, 3? 1, 2, 3 H is going to be a non-trivial left coset of this thing. So we'll have some calculation to do. We'll have 1, 2, 3. If I compose 1, 2, 3 with this, let's see. 1's going to go to 2, which is going to go to 3. 3 is going to go to 4, which is then going to stay put. And then, if I'm not mistaken, 4 is going to go to 3, which goes to 1, and so that ends up being that. Then when I compose this with 1, 3, 2, 4, 1 goes to 3, which goes back to 1, so 1 stays put, 2 goes to 4 and stays at 4. 4 goes to 2, which ends up going to 3. And then that concludes that cycle. And then for this one, 1 goes to 4, which stays put. 4 is going to go to 1, which goes to 3. So there are the 4 elements that are a part of this coset. I'm trying to do this calculation on the fly here. I think we've got it. And as we list more cosets, the work is going to get a little bit simpler, because now I know to get another coset, what elements should I not choose to represent this next coset? Anything that's already been represented. Because we know that every 2 cosets that I can pick of the same subgroup are either disjoint or they're exactly the same coset. Right? Cosets cannot overlap unless they overlap completely. So as long as I pick an element that's not already listed up here, I'm going to get a new coset. How about 1, 3, 2? So here I'll get 1, 3, 2 as an element. I want to try not to take shortcuts here if I can avoid it. 1's going to go to 2, and 2's going to go back to 1, so that stays put. 2 goes to 1, which goes to 3, so that's 2, 3. 3 goes to 4, which then stays put, so we have 2, 3, 4. This composition, 1, 3, 2 with 1, 3, 2, 4. 1 goes to 3, which goes to 2, so 1 goes to 2. 2 goes to 4, which stays put. So I think we're just going to have 1, 2, 4 there. And then finally, 1, 3, 2 composed with 1, 4, 2, 3. 1 goes to 4, which stays at 4. 4 goes to 1, which then goes to 3. So we have 1. Uh-oh. No, that can't be right. What am I screwing up here? 1 goes to 4, and then 4 goes to... Oh, this is 1, 4, 2 here, isn't it? Yeah. Sorry. That's what I mean about doing these calculations on the fly. There we go. So I knew that was a mistake, right? Because we can't have the same element belong to two different cosets. All right, so now we have no more overlaps. So that's looking good. And so now to get my final, by the way, how do I know that this last coset is going to be my last coset? How many elements are in the subgroup H? There's 4 of them. How many elements are in A4? 12. So what we're doing here is we're building a row by column table, right? That row by column table that we use to explain why Lagrange's theorem is so significant, right? That we're making this row by column table, and we're going to make a table in which every element of this group, A4, is listed exactly once. So if my columns each have, if my rows each have 4 elements in them, then that means, then that means that I actually don't have another coset, and I counted wrong, right? Because now I've listed all 12 elements in my group in a 3 rows, 4 columns table. Every element here appears once and only once. And this is the mental model, by the way, that for me really unlocked the meaning of this whole body of ideas that we're talking about in this last act of our course. Right? The act of listing A4 into a row by column 4 by 3 table of elements actually is going to tell us, for me, this is the mental model that explains this last bit of stuff that we're doing. So I'm going to recopy it down here just so I have a fresh copy. So in my first row, I have my subgroup, which has identity, and it has each of these 2, 2 cycles. 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. And then my second row had the coset of 1, 2, 3. And so that contained 1, 2, 3. It contained 1, 3, 4, 2, 4, 3, 1, 4, 2. And then my last row, 1, 3, 2, 2, 3, 4, 1, 2, 4, and 1, 4, 3. Whew. All right. So here are all of the elements of A4. Let me color code this rectangle here. Here are all of my elements of A4, but arranged as the cosets of the subgroup H. So let me get H in this picture one more time. So I'm going to write H sort of up here. It's the identity. It's 1, 2 composed with 3, 4. It's 1, 3 composed with 2, 4. And it's 1, 4 composed with 2, 3. So here's the shift in our ways of thinking that is going to power the week. The first shift is I want to start thinking about subgroups and normal subgroups as being related to functions. And so what I mean by that is I want to think of this subgroup that we started this problem with here. I want to think of it as the image of a function. Right? So I have a function whose domain consists of 4 elements, and I want the images of those 4 elements to be these 4 elements of A4. Well, what do we know about these elements of A4? What's the order of the identity element? 1. What are the orders of these other elements in A4? 2. So I have a group of order 4, one of whose elements has order 1, the others have order 3. What other group of order 4 do we know that acts like that? 4 elements, 3 of them have order 2, 1 of them has order 1. We can check, by the way, that also all these elements commute one with another. So I have an abelian group of order 4 that does not have an element of order 4, but it does have elements of order 1 and 2. What does the fundamental theorem tell me? This is actually how we ended our last class also. Group has order 4, it's abelian, but it's not cyclic. You can think of that as a direct product of Z2 with Z2. So that's my first shift, is I kind of want to think of this subgroup as being created by taking some other group from the outside and just sort of plunking a copy of it down inside of A4. And this copy should have the same properties that this had. Well, what kind of functions connect a group to another group that has all the same properties as it? Isomorphisms, right? So what I want is I want a function here that is an isomorphism. It's an isomorphism from Z2 direct product Z2 onto this subgroup, onto H, right? So this shows that H is isomorphic to Z2 plus Z2, right? But, and here's the beauty, right? Because H is a normal subgroup, we also can think of these rows. These rows are identity H, 1, 2, 3 H, and 1, 3, 2 H. We can take these rows and we can treat the rows as elements of a new group. Right? That was what normal subgroups are supposed to do for us, right? It's supposed to let us think of the cosets as elements of a group themselves. And so here is a picture of what that might look like. That's a picture of taking these elements and mapping the rows across into a new group over here, and that group is going to have how many elements? A group whose elements are the cosets of H and A4. 3 elements, the same as the index of the subgroup H inside of A4, the number of cosets. Right? I realize that that's a term that we haven't stressed enough, so let me do it now. Right? So index of a subgroup, the index of H in G, this is just equal to the number of cosets that H has. And according to Lagrange's theorem, this is just equal to the ratio, right? It's the number of elements in my whole table divided by the number of columns in my table. The order of G divided by the order of H. A4 had 12 elements. My subgroup had 4, and therefore it falls into 4 columns and 3 rows. So the claim is, if the cosets form a group, then this thing over here can be thought of as a group. And that these representatives, so the identity element, H, is one of my elements. 1, 2, 3 H is another one of my elements. And 1, 3, 2 H is another one of my elements. That when I multiply one of these by another, I can do that just by multiplying together the 2 representatives. So for example, if I took 1, 2, 3 H and I multiplied it by 1, 2, 3 H, what am I supposed to get? Red times red. Well, because H was a normal subgroup, I can multiply the 1, 2, 3s, the representatives. 1, 2, 3 times 1, 2, 3 times H. But what is 1, 2, 3 times 1, 2, 3? This is an element of order 3, and so its second power is its inverse. Its inverse is 1, 3, 2. So red times red is going to give me blue. Right? Here's my point. I'm running a couple minutes over here, so I better make my point quick, and then let us all go for today. Here's my point. My point is, if we wanted to make a Cayley table for these 3 cosets, that's how we introduced factor groups before. One way to do it is just by taking the original Cayley table of A4 and just dividing it up in the way that we did on the group assignment in class. And if we did that, we would get this whole chunk here, which is my identity coset. Identity times H. Identity times H. I would get another chunk, which is my coset of 1, 2, 3. It would go here. Right? So this would be 1, 2, 3 H. 1, 2, 3 H. And then I get one more chunk, which would be 1, 3, 2 H. But here's the point, last but not least. The point is that in a factor group of a normal subgroup, the cosets act exactly the way that their representatives act. What I mean is, there's no difference between how 1, 2, 3 H interacts with itself as a coset than there is in how the element 1, 2, 3 acts with respect to itself. And that is a fancy way of saying that I might as well make the following Cayley table instead. Just forget about the H's. And just worry about the representatives. Identity, 1, 2, 3, 1, 3, 2. If I make the Cayley table with those three permutations, then that Cayley table structure will be the same thing as the Cayley table structure of my group of cosets. Right? Identity times identity is identity. Identity times 1, 2, 3 is going to be 1, 2, 3, 1, 3, 2, and so forth. And the fact that these ended up being cosets is blurred in the process. We don't care. Identity, 1, 2, 3. So, here's how it's going to work. This factor group over here is a group with how many elements? Is it abelian? Is this group here, identity 1, 2, 3, 1, 3, 2, abelian? Is it cyclic? It is. What's a generator for this group? 1, 2, 3 generates this group. This is indeed the cyclic subgroup generated by 1, 2, 3, or by 1, 3, 2, either way, right? So this group is cyclic. It has 3 elements. To what group is it isomorphic? Cyclic group of order 3. Z3. Yeah, exactly. So at the end of this process, what we can say, this was the last question on the quiz, right? That even if all we knew was that this group had 3 elements, that should have been enough, because 3 is prime, and every group of prime order is cyclic. Right? So automatically, even without doing the rest of this structure, we could have known that this group is Z3. But, and this is where I'll end for today. I keep saying that. This time it's true. We want to focus again on using functions to do this grunt work for us when it's less easy of a question than it was here. And there's going to be 2 functions doing this lifting for us. There's going to be an isomorphism that takes a copy of my subgroup and plunks it down into my big group, right? Kind of gives me my first row. And there's another function that's going to take that whole group and sort of smush it down onto this factor group. Problem is that function is probably not an isomorphism. Because, for instance, this function is not one-to-one. Right? All 4 of these different elements end up going to the same spot. So it's not one-to-one. It does end up being onto. But most importantly of all, it respects the structure of this group. And so we will call it a homomorphism. And the goal is going to be to use homomorphisms out of a group to be able to understand where normal subgroups of that group come from, and simultaneously to understand the factor groups by those normal subgroups. So if you give me a homomorphism out of my group, I can provide for you a normal subgroup by taking the kernel of that homomorphism, and via the first isomorphism theorem, I can also tell you what the structure of that factor group is. So this little diagram is where we will pick things up on Wednesday.